Yeah. Yeah. Okay. So it's my pleasure to welcome Marian Mrozek, who will be talking about topological methods in sample dynamics. Yes. So thank you.
Thank you, Boumediene, for the invitation. It's a pleasure to have a talk in Imperial College again. Although it's a pity it's only virtual, I remember my visit in 2007, when I had a couple of lectures there. I hope the normal times will come back soon, but for the moment, that's also okay. And actually, it's surprising that it works, that the technology helps to resolve the situation. Okay, so today I'd like to summarize a few years of my and my colleagues' research, where we try to bring topological methods into the problems in big data, and particularly in dynamically driven data, so where you have just samples of dynamical systems. So this is based on joint work with several people. I will not read all those names, but these are all either my colleagues or my students or my younger collaborators. And without their work, actually, I would be not able to present what I intend to present today. So not everybody remembers, even some topologists do not remember that Henri Poincaré invented topology as a tool to study dynamical systems. So the subject became very soon very interesting to many mathematicians with many, many deep problems of its own. And it was for some time forgotten that it was particularly algebraic topology. It was just, at least by Poincaré, invented as a method to study difficult problems in dynamics. But sometime in the middle and second half of the 20th century, the people working in dynamics went back to the origins, and several tools were invented. And I also mentioned here a few of those which are particularly of my interest around the Warzewski theorem and Conley index. But they were invented just to study classical dynamical system. And by this, I mean dynamical system coming mainly from differential equations, maybe from iterates of maps, but not dynamical system known only for samples. And so this is just a few examples of problems where just the source is just the data. It's so easy nowadays to collect data, in particular dynamical data, and it's natural to try to understand this as I call them, sample dynamical systems using the existing methods. But sometimes it's not immediate how to adapt the existing methods to work with these kinds of problems. So the outline of my talk consists of just 3 pieces. In the first part, I want to briefly recall those topological invariants in dynamics I am interested in, and those which I want to use in the context of data. And then I'll just switch to what I call combinatorial topological dynamics, where I give a kind of general attempt to study dynamics based. Sorry, I have to, one moment, let me just turn off my mail program because it'll interfere. Okay, sorry. Okay, so in the second part, I give the general overview of these topological methods applied directly to data. And then in the third part, I'll concentrate on a very special case motivated by the Forman's concept of combinatorial vector field.
Yeah, sorry, but I think you froze a bit.
Sorry, can you hear me? Can you see me?
Yes, yeah, now you are back, yeah.
So I hope it works fine. I'm connected by hardwire. So in general, my internet connection is fine. I hope it will work. Okay, so the general question of mathematical modeling of dynamic processes, as I said, historically goes back to differential equations, autonomous differential equations, and also iterates of maps. So when you do that kind of study, it's assumed that at least explicit formulas are known either for the vector field V or for the map F, but not necessarily for the solution. So that the ideal situation is that you can derive the formulas for solutions from the formulas of the dynamical system, but generally this is difficult. And the theory of dynamical systems attempts to study the asymptotic behavior of dynamical systems based on the knowledge of the equations themselves, but not on the knowledge of formulas, which are usually difficult to obtain in a closed form from the right-hand side of the differential equation, for instance. So just to fix notation, by a dynamical system on a topological space, I mean a continuous map from a topological space X cross a set of real numbers or integers, or even non-negative real numbers or non-negative integers. I just denoted by this blackboard capital T. And these are the usual axioms of a dynamical system. And I'll be interested in these three concepts: the concept of a solution. So whenever you have an X in the space, topological space X, then I can look into the map which sends time t into the dynamical system starting at X after time t. So this is a solution. This is different from the trajectory, which is just the image of the solution. So the set of all possible values along the trajectory. And I'll be also interested in time t map, where I fix t, and now I have a map from X to X, which sends each point X to its position after time t. And as I said, the goal of so understood topological dynamics is the long-term behavior of solutions by means of topological invariants. And at the very beginning of the theory, I want to recall here the Conley theory is the Warzewski theorem. Warzewski was a mathematician here in Krakow. He died the same year as I started my mathematical studies. It was 1972. I had unfortunately, no opportunity to meet him in person, but I met many his students who were also my teachers. So let me recall his theorem. So let's say we have a dynamical system on a topological space X, and we have a compact set N, and then we look into the so-called exit set. So these are the points in N such that when you look for the future, the immediate future, after a short time, then they are no longer in N. So here is a picture. So for instance, this is my N. You have just a few trajectories drawn here. We do not know what happens here inside, but we understand the behavior along the boundary, and the exit set for this set N is marked here in red. For this concept of exit set to work, you need the time to be real, so continuous dynamical system or flow. But there are analogous concepts, slightly technically more complicated when the time is discrete. Okay, and now, so this is Tadeusz Warzewski. And his theorem says that if you have such a compact with its exit set n minus closed, and this exit set is not a deformation retract of n, then there must be a point in n whose whole trajectory is in n. So the deformation retract, a subset of X is a deformation retract if there exists a continuous map R from the whole space into the subset, which is homotopic to identity on X, and the homotopy must fix the points in A. So it's easy to imagine that in this case, such a deformation retract is not possible because N is connected and the exit set is not connected. So if such a continuous map was possible here, fixing the red set, then it would have to break the connected set into two pieces. So that's clearly not possible, which means that in this simple example, actually there must be a trajectory fully here inside. Of course, the theorem of Warzewski does not tell us anything about what the trajectory is. The simplest thing is, of course, to put a fixed point here and have the classical saddle. But actually, the situation here inside may be much more complex. So Charles Conley took the Warzewski ideas. Actually, the true story, as I learned from Jack Hale, was that Conley came to the similar ideas as Warzewski independently, and then when he presented some of his ideas at a seminar at Brown University, I think he was told that but one of the participants, maybe even Jack Hale, that this resembles the work of Warzewski, and this way he learned about. But of course, then later he quotes the Warzewski results in his paper. But Conley made an important change in contribution is maybe not enough because it's Conley make a whole machinery out of this simple Warzewski theorem. Namely, his first observation was that there may be two different situations when this closedness of the exit set fails. I have this in these pictures. So in both cases, the exit set is not closed. There is so-called internal tangency here. This trajectory comes to the boundary, but then does not go away, goes back inside, and this causes that actually the exit set, these points to the left are in the exit set, but to the right no longer in the exit set. So this point is in the closure of the exit set, but not in the exit set. A similar situation is here, but still the two pictures are significantly different. Namely, the trajectory which is tangent here goes away from set n after some time. So it exits in forward time, or it might exit in backward time, whereas in the left picture, there is a periodic trajectory, which causes that actually the internal tangency never leaves. So Conley distinguished these two cases by introducing the concept of an isolating neighborhood. Namely, he looked into the maximal invariant subset of n. This is defined as the collection of all points whose full trajectory sits in n. So this dark disk here is the invariant part of n, and also it's here. And you see its location is different. In the left picture, it's tangent to the boundary, this invariant part. In the right picture, it's contained entirely in the interior of n. So when you see the situation that this invariant part does not, the maximal invariant subset, in other words, does not intersect the boundary of n, then Conley says that this invariant part is an isolated invariant set. So to the left, to the right, you have an isolated invariant set as this dark gray disk. The dark gray disk is invariant in the left picture, but it's not isolated in the left picture. And then just not going into too many details, let's say that an isolating neighborhood is an isolating block. Okay, maybe I didn't, let me go back. Okay, so the N is an isolating neighborhood. Actually, the right one is an isolating neighborhood, and the invariant part inside is the isolated invariant set. Isolating neighborhood need not be invariant, but the maximal invariant subset is isolated if it is disjoint from the boundary of the isolating neighborhood. Okay, and then there is this special case when you have an isolating neighborhood, and moreover, as in the Warzewski theorem, the exit set is closed. In that case, Conley and his student referred to this situation as a special isolating neighborhood. They call it isolating block. And they proved two fundamental for the whole theory theorems. Namely, for every isolating neighborhood, there exists an isolating block which is contained in the isolating neighborhood, contains the isolated invariant set. And whenever you have, so there may be many such there is at least one, actually, usually there are many such isolating blocks inside. And when you have two of them, then when you do this topological operation of smashing the exit set to a point, so just think about, you take the isolating block and you glue all the points in the exit set to one point. This way you get so-called pointed topological space. So this glued set is just the distinguished point. And when you do such an operation of two isolating blocks, then the results are homotopy equivalent. And this is this theorem allows Conley to define what is today known as the Conley index. In its most general form, it takes the form of the homotopy type of this quotient space with a distinguished point. But in terms of practical computations, usually one uses homology theory, and then one can show that instead of taking the quotient space, you can take the pair, the isolating block and its exit set. So this is a closed set, a compact set, and its closed subset. The relative homology is independent of the choice of the particular isolating block, as long as the isolating blocks isolate the same isolated invariant set. And by the definition, this is the Conley index. And how does it work? Why is it useful, this Conley index? Maybe one more definition. In the simple situation, it's very convenient, particularly in pictures, to represent the Conley index as the Conley polynomial. Namely, in particular, when you take just field coefficients for the homology, then this is a graded vector space. In every grade, you have the respective Betty number, which is an integer. And actually, up to an isomorphism, this Conley index is just this collection of these Betty numbers. And typically, it's written as the polynomial. It's convenient to avoid the question, what is the last non-trivial Betty number? One can prove that only finite number of them is non-zero under mild conditions about the space and the isolated invariant set. And so you write this up to infinity, but in practice, this is a polynomial. Okay, so let me go to some examples. So this is the case when actually the assumptions of the Warzewski theorem are only partially satisfied. Namely, the exit set here is clearly closed, but it's the exit set actually is a deformation retract. You can use just the flow along the trajectories. You can just squeeze everything to this point, and so the homotopy type of this pointed space is just the same as the homotopy type of the point. And this is just the trivial Conley index. The trivial Conley index is the situation when you cannot use the Warzewski theorem because there exists actually a deformation retract. But here is our earlier example with the saddle. Here the computation may be done in a few steps. Sometimes mentally it's more easier first to glue the top part independently and the bottom part independently to two points, but they still need to glue those 2 points together into 1 point. So then you have to bend this a little bit. Then it looks like this. And then when you take the homotopy type, then actually it results in, it's the same as the homotopy type of a pointed circle. So this is the Conley index of the saddle. And this is, again, and now it's non-trivial, which means that actually, since it's non-trivial, it means that it's not possible to have this deformation retraction. We already realized that earlier. For that, you do not need homology. It's just the counting of connected components enough. But of course, in more advanced problems, homology is useful because not everything may be reduced just to counting connected components. And here, this is our first example. This is the Conley polynomial is 0 because the homology is 0 here in this case. This is our saddle. The homology is non-trivial only in dimension 1 when you take the homology of a pointed circle. So because it's relative homology to the point, the 0 homology vanishes. The first homology is non-trivial and all other homology vanish again. So the Conley polynomial is T. For this example, which is an attracting fixed point, the exit set is actually empty. There is nothing going out. This is an attracting fixed point. In such a case, the empty set is still glued to a point, which means that what you get here is a 2-point space with 1 point distinguished, which results in non-trivial homology in dimension 0, and the Conley polynomial is just 1. Maybe let's look into one more example, maybe this one. This is a repolling periodic orbit. The exit set is just 2 circles on the boundary. So this is a mental exercise to see what happens when you glue these 2 circles to a point. When you use also the fact that you are only interested in the space up to homotopy type, you can deform it to a wedge of a 2-dimensional sphere and 1-dimensional sphere. So a sphere and a circle, which means that the non-zero Betti numbers are in dimension 1 and 2, and then the Conley polynomial is T plus T squared in this case. Okay, so these are some examples, and here are the main properties which make actually the Conley index useful. So the simplest one is just the rephrasing of the Warzewski theorem. Whenever the Conley index is non-trivial, and non-trivial means different from this pointed point, which has homology 0, then the maximal invariant set inside is non-empty. But there is more. If you compute the Euler characteristic of this homology, and this Euler characteristic is non-zero, then actually there exists a fixed point, a point whose trajectory is just 1 point. So this is as in our example with the saddle. And here it's easy to see that for this example, the Euler characteristic is also non-zero because it's an alternating sum, but all the terms are 0 except 1, which is non-zero. So the alternating sum must also be non-zero, which in this -1 in this case, which means that actually this fixed point. So even if you try to put a complicated dynamics here inside, you cannot avoid putting at least 1 fixed point there. So this is the Hopf property. Then the additivity property, if your isolated invariant set may be decomposed as the union of 2 isolated invariant sets with empty intersection. This is a mistake here. Sorry. This should say equals to 0. No, not equal, but equal to 0. Disjoint. Then the Conley index of S is a direct sum of the Conley indices of the two pieces. And this is often used to prove so-called heteroclinic connections, the existence of heteroclinic connections in dynamical systems. And another important property, which is used in analytic computations of the Conley index, when you have a family of flows continuously depending on an additional parameter, your n is an isolating neighborhood for every of these flows, then actually the Conley index cannot change. As long as you keep your n isolating neighborhood and you modify your flow, the Conley index is not changed. So analytically, often you start with a dynamical system, you try to modify it to a simpler one where it's easier to construct an isolating block and compute the index. Because in general, in terms of applications, the hard part, the relatively easy part is to identify an isolating neighborhood, but knowing an isolating neighborhood is not enough to compute the Conley index. If you have an isolating neighborhood, you only know that the index is well defined. But then you need an isolating block if you want to directly, by definition, compute the index. And finding an isolating block is typically much harder. So in analytic approaches, often you just try to modify your dynamical system to another one where it's easier to find an isolating block. And then you only, when you modify, you have only to look at the boundaries so as to make sure that the modification does not violate the assumption then n is all the time an isolating neighborhood. Okay, so there is more to that, namely the concept of Morse decomposition. This is actually a generalization of the classical Morse theory to the setting of flows. So a Morse decomposition of an isolated invariant set is a finite collection of isolated invariant sets indexed by a poset P, such that for every point which is in your isolated invariant set, but not in one of these isolated invariant sets in the collection, then actually this point must be on a heteroclinic connection between a set with index Q, which is greater than another set in the collection with index P. Usually these sets in these collections are referred to as Morse sets. So whatever else is in this invariant set, not in one of the Morse sets, must be on a heteroclinic connection from something which is higher to something which is lower. So here is an example. So this is an isolated invariant set, this disk, gray disk. And the Morse sets, there are 4 Morse sets. I marked them S1, S2, S3, S4. So 3 of them are just fixed points. This fixed point is always an invariant set, and in this case also isolated invariant set. It's easy to see that a small closed neighborhood is always here an isolating neighborhood for those fixed points. The 4th one is actually a periodic orbit, but it's also isolated invariant set because a small annulus around this orbit is an isolating neighborhood. And anything else, for instance, when you pick up a point here in this gray set, then it's when you go backwards along the trajectory, then you limit in the periodic trajectory. When you go forward, you limit in the fixed point, and this applies to any other point here. For instance, this one, when you go backwards, limits in the saddle stationary point. When you go forwards, it limits in the red attracting fixed point. To the Morse decomposition, one associates an invariant called Conley Morse graph, where you have your poset or your Morse sets ordered by the poset. So these arrows indicate the poset relation, and you put labels at the individual Morse sets in the form of their Conley polynomials. This is a generalization of the Morse theory because actually in the Morse, every gradient flow on a differential manifold satisfying this assumptions needed for the Morse theory so that the fixed points, the zeros are isolated and non-degenerate, then the critical points of this functional actually form the Morse sets. Each Morse set is just a point, a stationary point. And the Morse index, so the dimension of the unstable manifold, is related then to the Conley index, because you can show that in such a situation, when you have a non-degenerate fixed point, then its Conley index is non-trivial only in one dimension where it's just z, and the dimension is just the Morse index of that fixed point. There is another interesting story about this Conley, about this Morse decomposition, namely the concept of a connection matrix. Let me only mention the definition is rather complicated. I'll not go into the details of the definition here, but the connection matrix is actually, in the case of the classical Morse theory, it reduces to the boundary operator of this Morse complex, this artificial chain complex constructed from the critical points and the boundary map defined by in terms of the connections, as in the classical Morse theory. So this generalized to the idea of connection matrix for the Morse decompositions in Conley theory. And again, these individual entries here are responsible for the existence of connections between the individual Morse sets. Okay, and in this setting, you can also prove, as in the classical setting, the Morse inequalities, but instead of counting the critical points of a given Morse index, you just take the sum of the ith Betty number of each Conley index of the Morse set. When you take the sum of these Betty numbers, then it's greater or equal to the Betty number of the isolated invariant set whose Morse decomposition you study. Okay, so this was a brief recall of the Conley theory for flows, and it was used in several papers to prove various dynamical phenomena. In particular, it was very broadly used to prove the existence of heteroclinic connections in dynamics, but also to the existence of chaotic invariant sets, and I'll go back to that in a moment. Now, very briefly about a variant of the Conley theory for maps for dynamical systems with discrete time, where our capital T is just non-negative integers. So then the concept of isolating block is replaced by a more technical concept of an index pair, where the first element in the pair plays the role of an isolating neighborhood, and the second element plays the role of the exit set. I will not give here the definition. There is one novelty here, which is not present in the classical theory. When you have an index pair and the respective homology, the generator of the discrete dynamical system, so the time one map, the map which generates the discrete dynamical system, also induces a map on this homology. And the Conley index is obtained by quotienting out the generalized kernel of this index map. It turns out to be necessary, something which is not needed in the flow case. So several people proposed these various variants of this construction of the Conley index for maps. Let me only mention here that when you take a time t map of a flow, so you can always, when you have a flow, you can always extract from it a discrete dynamical system by fixing a t and taking the multiples of this t so the powers of this time T map as the discrete dynamical system. But then such a map is always homotopic to identity, and since it's homotopic to identity, it causes this index map in such a case is always identity actually. And since it's always identity, it's general's kernel, which is the union of the kernels of iterates. Sorry, this is again a mistake here. This should be just the sum of the iterates of the powers. Then the identity has no kernel, so you have nothing to quotient out, and this way you go back to the classical Conley index. So in that sense, the Conley index for maps captures the case of flows as a special case. Okay, so let me recall the result which I had the pleasure to prove several years ago with Konstantin Mishaikov, which was probably one of the first attempts, now there are many more by several authors, to use the Conley theory not analytically, but to compute the necessary Conley indices by the help of the computer. We use this to prove the existence of chaos in the Lorentz system. And the proof was just the Conley theory applied to the Poincaré map. You can just construct there a Poincaré section, and we studied the Conley index of this Poincaré map. But to compute the Conley index, there was no chance to do it analytically, and instead we made a finite sample, which means that we collected the finite amount of points on the section. And for those points and their neighborhoods, we found rigorous enclosures of the Poincaré map. We used for that interval arithmetic. And it turned out that this way we constructed what we call today a combinatorial multivalued map. And this combinatorial multivalued map was actually used again algorithmically to construct an index pair, to construct an index map, and to compute the necessary Conley index. Okay, and I have a reason to recall this result because actually I never used this terminology earlier. I never thought at that time this way about what we did at that time, that we actually did this finite sampling of the Lorentz system, but it was combined with these rigorous computations, which turned out that this showed that actually this finite sample was enough to make a computer-assisted proof. So in principle, there is no obstacle, no fundamental obstacle, but of course, details are, as usual, a little bit complicated. But it seems there should be no fundamental obstacle to do the same for dynamical systems known only from a sample, where you have either no differential equation or a poorly understood differential equation. Okay, so now to the second part of my talk, how to use topological tools in sample dynamics. So what I mean by a sample dynamical system, it's a dynamical system which reveals itself only through a finite data set coming either from observations or from experiments, or even from evaluations, as in our case of the computer-assisted proof of chaos in the Lorentz system. Nevertheless, there is a significant difference when you have evaluations, then at least you can always hope for making more evaluations. If you feel the evaluations you have are not enough to make rigorous claims, you can always at least try to make more evaluations. It's there in case of observations or even experiments, it's often much harder or just impossible. You have just a set of observations done by somebody and that's it. The time is gone and there is no way to repeat these observations. And you have just this data set and you just try to draw as much as possible from what you have. Okay, so what people do often, and this is a very natural course of action, is that they take the data and they try to approximate it by a regular function and then try to investigate the associated classical dynamical system, because then this approximation has a closed formula and you can make numerical experiments and also try to prove something analytically about the system you obtain this way. But there is an alternative, and why to think about the alternative? So my argument is as follows. When you're just given data and you have no knowledge at all what are the principles governing your dynamical system, which means that even if you write an artificial polynomial for the right-hand side of the equation and you just try to fit your data to the unknown coefficients, and probably you have to take many of those coefficients to get a reasonable fit, then, okay, you obtain an artificial differential equation with no understanding why such a differential equation, it just fits the data, it's all. And then you discretize again, because typically once you have a differential equation, there is no way to solve the problem analytically. So you again discretize, you do numerics, but you discretize something which originally was already discrete, your set of data, discretize in another way, and then you try to use this bridge via the differential equation to relate your results back to the data. That's understandable if there is no other choice, but at the same time, it's natural to try to eliminate this differential equation, and then it try to build what I call a combinatorial model. Something like an analog of a dynamical system acting on a finite space, on a combinatorial space. I call it a combinatorial dynamical system, and try to adapt the tools you have from the classical dynamics to this new setting. And this is what we try to do. And from the very beginning, let me emphasize that there are two flavors of the sample dynamical systems. So you have your data set. This may be typically represented as a collection of vectors sitting in some n-dimensional space. For pictures, usually you just draw something on the plane, but typically this is in higher dimension. And then on top of that, you have an action of a map, which tells you that this point under the observed dynamics goes either directly to this point, in practice, probably not directly to this point, but somewhere nearby, and you just choose the nearest point because you have to set up some finite set anyway. And this more or less represents what we would call a dynamical system with discrete time. The other flavor is when you again have a collection of points, a cloud, as people in topological data analysis say, a cloud of points. And for every point, you have a vector indicating the direction where the dynamical system may evolve. You can think of such an experiment that you go through the oceans. You have randomly chosen points in the ocean, and when you just measure the current at that given moment, and you record this, your measurement in the form of the vectors. So you have a sample of vectors from your dynamical system, and this more or less represents a sampled flow, a dynamical system with continuous time. So we'll see that actually more, so far we can do more for this second flavor, which seems somehow to be a little bit simpler, but nevertheless something may be done in this more general setting too. Okay, so first of all, before you try to define what your combinatorial dynamical system is, you have first to define some reasonable space, because the finite collection of points, it's not a topologically interesting space. So you need to put some reasonable topological space on top of that. And I will not go here into the details. There is now a huge area of research called just topological data analysis, which addresses that kind of problems. Very briefly, there are several methods. I'll only concentrate on two. One is a kind of Rips or check complex, which is to the left. And the other is what we call binned approach, where you just take a kind of regular grid and you take out of this grid only those grid elements where you have at least one point. in the grid. So you have these two constructions from the same data set, and at least you see what also a human brain probably captures here, that the shape of this data set is something like annulus. So you see it both here and here, this topological annulus in both space reconstructions. Okay, so let me speak first about this triangulation, the first kind of space reconstruction. So what people do is either they construct Rips complex or check complex. In practice, you pick up a measure, a distance, you fix a distance, and you put a disk at every point in your cloud of diameter not greater than epsilon. And then you build a symmetrical complex whenever either in the form of the Rips complex, whenever such two disks intersect, and then you keep adding higher dimensional simplices whenever the lower dimension, all the edges are present, then you also add the higher dimensional simplices. And more advanced, but also more difficult in practice is computationally difficult, is the check complex, when you actually really not only check the intersection of two disks, but to put a triangle, you check whether there is non-empty intersection of the respective three disks and so on. And of course, the big question here is what the epsilon should be, because your result will clearly depend on the epsilon. And for that, there is this persistent homology, which was invented by Herbert Edelsbrunner in the paper very end of the 20th century, very beginning of the 21st century. The idea is, instead of fixing one epsilon and just guessing what the right epsilon should be, take all the epsilons and construct all the simplicial complexes, and then watch what happens when you grow your epsilon. So you start with when epsilon is 0. It's not in this picture, by the way. This is a great paper by Rob Grist, which let me use his figures in my talks, and the paper is in Bulletin of the AMS. You start with the collection of points where epsilon is 0, and then gradually certain vertices get connected, and then even you see some closed loops. Then certain triangles are filled and so on. And eventually, when the epsilon is very big, then everything is connected. You just get something homotopy equivalent to a point. But then you may look when homology generators are born and when they die. And because, for instance, here you see that there are these two closed loops present, and they are marked here. Maybe they were born a little bit earlier, but later on, for instance, this one, when you look at this picture, it's no longer present because you also added triangles here. So you glued that loop, which means that this one already died here. The other one dies a little bit earlier. Here it's already gone, and so on. And then you say, whenever I have a short bar, this is noise. Whenever I have a long bar, this is something present. This is a feature. This is something which is really present in the data. Okay, so when I mentioned this computer-assisted proof, there you can combine it with these rigorous computations, which gives you trust with that you really have a mathematical proof. When you start with data, then there is no hope to do anything rigorously. There is just data, and you need another method of validation. And this other method of validation, a natural choice, is just taking this persistent homology mechanism. If you see that the same happens when you vary a parameter, and for a reasonably long stretch of that parameter, you see the same, for instance, the same Conley index, then probably it's reasonable to expect that in the dynamics you observe via the sample, you really have an isolated invariant set with this Conley index. So this is, of course, what we would like to do, but it's not so entirely obvious how to combine all these ideas. So you can do something using this triangulated approach in terms of finding the homology of the generator of the dynamical system. So for instance, so now you have, let's say this is my Czech or Rips reconstruction of the space, this triangulated, this simplicial complex. But I'll go now back to my information about the dynamical system. So let's say I know that this point goes to this point, and this point goes to this point. And I'd like to use then this information that this edge should go to something which connects these points. The easiest way would be just to, for some reason it's not well visible, but I just wanted here to, oh yes, now it should be. So this is now these three blue edges which make the connection between the 2 points. So in terms of the chain representants, you could say that this edge is mapped to this chain which connects the endpoints. And you could hope that this way you could at least reconstruct the chain map, and from the chain map, the map induced by in homology by your generator. But there are problems here. We managed to some extent to resolve these problems in my work with Edelsbrunner and Uli Bauer and my student Grzesiek Jabłoński in these papers. But so the problem with this is that we see how to do persistence in this setting, how to understand the behavior of this homology generator in the flavor of persistence. But so far we have no idea at all how to do Conley theory in this setting. So since my time is passing, maybe I skip the details. Maybe only mention very briefly here in this figure is that actually to do persistence, we need to introduce an artificial space. And actually, instead of looking into a self map, we look into a pair of maps. For such a pair of maps, the concept of eigenvalue and eigenspace is also possible. But you can no longer do dynamics because it's no longer a self map. So you have persistence. From that persistence, you can actually get the knowledge about the eigenvalues of your homology generator, but there is no idea how to go on with that into the Conley theory. So let me skip that. Very briefly to the bind approach. So now you have this other space, the collected. So your grid is now fixed, and you only keep those grid elements where you have your data points. And here you can construct something like a multivalued map, similar actually to the multivalued map we used in computer-assisted proofs. So for instance, here in this box, you see that there are 2 points in this box. One goes to this box, one goes to this box. So you say, okay, so I should have a multivalued map which sends every point of this box to the collection of those 2 boxes. But the collection of those 2 boxes is not connected, which is not good for homology theory. So actually, you also have to add something to make it connected artificially. We saw that in this other approach, we had here this chain connecting these points. So we do something similar here. And this leads to what we call a representable multivalued map. So we use that for continuous maps. So for instance, for the Poincaré map in the Lorentz system, we constructed such a cubical cover of the graph rigorously. And for such maps, you actually can compute homology, and you can prove that the homology of this multivalued map, which may be computed algorithmically, that this homology also applies to the continuous map you're interested in. So in principle, you can do the same here, but there is one fundamental obstacle which makes things slightly different than in computer-assisted proofs. As I said, when you just have a data set, typically it's not fair to request more points. You can do more computations when you have a formula, but if there are experiments, if there are observations, either they're impossible or just too expensive to ask for more points. So you may be in the situation, so this is of course oversimplified to explain what's going on, that you have just 4 points on your, this is just a graph of your map. So the space is now one-dimensional for the sake of understanding the picture. And you collected just from your observation 4 points which on the graph. And then when you want to cover them with these boxes, as we did in the previous picture, clearly you get the same problem, which I already mentioned, the discontinuity, the two connected components in the value here. When we have a continuous map, then actually we also add these boxes to cover these pieces of the map. By the way, this is bad because this way we have a multivalued representation, but not very useful because this one cannot capture the isolated invariant sets, which is for this map here at 1/2. And what you actually want is this kind of representation where you just to this picture add only one horizontal line here. So only the value at this point is the whole interval. But here you keep this as before. But in this case, there is no longer a continuous selector as here, which means that actually Conley theory cannot be applied as we did in the computer-assisted proof for the selector, and only the homology computation was from the multivalued map. We need a Conley theory for such multivalued maps without continuous selectors. This was fortunately done recently in my paper with Bogdan Batko, and then we showed with Konstantin and my other student Mateusz Przybylski that actually you can use the kind of Conley analysis based just on data sets and this theory of Conley adapted to multi-valued maps without continuous selectors. Okay, so we see at this stage that the combinatorial dynamical system manifests itself as a map on a finite set into itself. We see this essentially, let me go back here. You still can think about what's going on here on the whole interval, but your information using computation is just the information that this box goes to the union of 3 boxes, this point goes to the union of 4 boxes, and so on. So this is all information on the finite space, on the finite collection of boxes. And it's easy to see that you really need a multivalued map. When you just would like to do classical dynamics and study only maps of finite sets, you cannot get anything interesting. It's easy to see that the dynamics of a map on a finite space is just a collection of periodic orbits, disjoint periodic orbits, no homoclinic connections, no gradient dynamics, no chaotic dynamics. But when you allow multivalued maps, then actually the wealth of dynamics is back. You can see the finite combinatorial models of most dynamical phenomena. So this is just one lessons we learned, that you can do combinatorial dynamics, but you have to think about it as a multivalued dynamics. Otherwise, you do not see interesting things. But what about topology? What can we do? One thing is what we did earlier. When you have those boxes, you can use topology of Rn because they are, on one hand, they are combinatorial, this collection of boxes, but as their unions are subsets of Rn, and you can use topology of Rn. But actually, it's not only interesting, but it's better for your intuition to switch into thinking about this space representations as posets. So you can have triangulation, you may have these sets, combinatorial sets consisting of cubes. More generally, you can have just CW complexes, cellular complexes, and they have this structure of a poset, namely via phase relation. So this is a very simple symplectic complex, and this is its associated poset. So the triangle ABC, has AB as its edge, so it's below. AB has A as a vertex, so it's below, so you get this poset. And there is this old Alexandrov theorem about today formulated in categorical terms as an categorical isomorphism between the theory of posets or even preorders and theory of topology on finite sets. There is an isomorphism, roughly speaking, and I will not go into details. The whole point is that you can translate concepts from topology to order or partial order or preorder and vice versa, particularly the concept of being locally closed. Probably you're more familiar with the concept of locally compact set because this is something common, but there is also concept of locally closed set, which is more or less the same, but replace compact by closed. And in this Alexandrov isomorphic corresponds to people in the theory of posets called convex sets. A convex set for a poset is a subset with the feature whenever 2 points are in the set, that everything between, but in terms of the partial order, is also in the set. So why this dictionary is important? Because actually when you use this topology on a finite space and you need to compute something, you just translate it to the language of posets, and then usually you have already ready implementations which you can use for solving your problem. And you may think that this strange topology may be far from the regular intuition, but it's not, at least in terms of algebraic invariants. There is this McCord theorem, which I'll not explain here in detail, but it actually says that whenever you have such a poset, then you can build an abstract simplicial complex consisting of all the subsets which are linearly ordered. And then there is a weak homotopy equivalence between the geometric representation of this simplicial complex and this finite topological space. Weak homotopy equivalence means that homotopy groups, homology groups are isomorphic. Okay, so that was this brief introduction to finite topological spaces. And now a definition: a combinatorial dynamical system is a dynamical system generated by a multivalued self-map on a finite topological space. So I explained why multivalued, and you can always take as X your collection of cells and use the classical topology of Rn. The only reason I mentioned the fact that it's useful also to use this finite topology, it's always equivalent in terms of topological invariants, whatever you use. But actually, when you start thinking in terms of this finite topology, you understand certain things which look strange at first, not like in the classical theory, but the explanation is that finite topological spaces are very tight. There is no Hausdorff axiom. The Hausdorff axiom in a classical, in particularly metric space, says that whenever you have 2 points, you can always find open sets which are centered at these points, which are disjoint. You cannot do it in a finite topological space unless this is a discrete space where every set is open. This is the only finite space with Hausdorff axiom. And this means that this space is tight. There is not so much room. And this means that certain technical concepts have to be defined differently. But what is beautiful here is that what is important goes through. Technicalities have to be set up differently. Okay, so actually there is Conley index theory for lower semi-continuous multivalued maps with acyclic closed values. I'll not explain what lower semi-continuous is for those who do not know, but this is just that for multivalued map, the concept of continuity splits into two concepts: lower semi-continuous, upper semi-continuous. So of course, some type of continuity is needed. This is work in progress. This is in principle done, but it's not yet at the stage what we have already preprint. So this is a work with Jonathan Barmack and Thomas Warner. And I will not go into the details, but using this work, we showed that actually you can do some kind of persistence for Morse decomposition in these settings. So this is a work with Tamal Day, Mateusz Juda, Tomek Kapela, Jacek Kubisa, and Michał Lipiński. This is already published. And first of all, there is a very simple observation, namely, you can always think about such a multivalued map as a directed graph. Your finite topological space, you may treat it as the set of vertices. And when you have a vertex X, you take the set of values and you put a directed edge. So like this, you have X here, and then there are a few points in f of X. So you just draw it as a directed edge, and this way you obtain a directed graph. So you can look into the collection of strongly connected components of this directed graph. And this collection forms actually a Morse decomposition. It's the finest Morse decomposition in this setting. Of course, to speak about the Morse decomposition, you still need X to be a topological space, because otherwise you cannot define this concept of isolated invariant sets and so on. Okay, so how can you do dynamics in this setting? So this is a very simple example again. So let's say I sampled a map on an interval with a large Gaussian noise. So this is really large Gaussian noise. And this is now this multivalued map made via this binned approach. So I have just two bins here, A, B, B, C, and their boundaries A, B, C. So this makes my finite topological space, which is also this poset. So A is a face of AB, B is a face of AB, and so on. And now my multivalued map, I do a modification, namely instead of putting an edge every time there is something in the bin going into another bin, I pick up a threshold. Namely, I put an edge only when there is a sufficient number of examples of such point. And depending on the choice of the threshold, the directed graph or the multivalued map may look different. So now I have this threshold which varies, and I have this collection of multivalued maps, and I can study persistence of Morse decompositions. So without going into the details, here is an example on a sample two-dimensional map, the Kuznetsov map. Sorry, I jumped quickly through its definition. So we sampled that map. It's easy to check that this map has a Morse decomposition consisting of a repelling fixed point at the origin and the attracting periodic trajectory. So there's this sample discrete trajectory, the yellow one, and one coming from outside, the blue one. And this is actually the so-called persistence diagram. There are two ways of representing the persistence, either via these bars, which I already showed, or you can just take the birth and death time as a pair of numbers and make a vertex in the, so this will be always in this upper triangle here, because death is always larger than birth. So you see, if I drew a bar here, you would have a bar which starts somewhere here and lasts up to here, so up to here. The color here represents the dimension. So there are two bars for zero homology. There is one bar for first homology among the bars which have a substantial length. There are many shorter bars which come just from noise. They are close to the diagonal. And this is how you see these Morse sets in this developing Morse decomposition. Okay, so this is that. And now let me go to the last part, namely to the cloud of vectors. Here you can do slightly more, because I showed this persistence of Morse decomposition, but in that case, we do not know yet how to do persistence of the Conley index itself. We only trace the topology, not the Conley indices of the Morse sets. In the setting of cloud of vectors, you can do more. We can do persistence of the Conley index and Morse decompositions. And here, there is another concept of combinatorial dynamical system, which is related to the previous one, but we still do not perfectly understand the relation. We more feel it than we are not able yet to formulate theorems. And this is based, okay, so this is now the reconstruction of space, again, a triangulation. And the concept goes back to Robin Forman, who presented more or less the same time as Edelsbrunner presented the persistent theory. Forman, at the end of the 20th century, presented a series of papers about a combinatorial version of Morse theory. And he proposed the concept of a combinatorial vector field on a collections of cells of a finite CW complex. There are several equivalent definitions. For us, it's convenient to think about it as a partition of this collection of CW complexes into a set of cardinality at most two, so singletons or doubletons, such that any doubleton consists of a cell and its face of codimension 1. So it's better to go to an example, but first a convention. So whenever I draw a triangulation, I'll also put a white disk at the center of mass of each simplex. So this one represents this edge, this one represents the whole triangle, and this one, of course, represents vertex B. So here is combinatorial vector field of Forman, which is a partition, because either you have a singleton, then it's marked as by a circle around this white vertex in the center of mass. So this means that just this triangle is itself one element of the partition. And then you have those doubletons, where I represent them by an arrow, because there is the condition on the doubleton. You cannot take any two simplices, but one might be the face of the other of codimension 1. So the difference in dimension must be 1. So for instance, a vertex and an edge, or an edge and a triangle, as here. And every cell belongs to precisely either a singleton or a doubleton. So this is really a partition. But there is a hidden dynamics here, multivalued dynamics. When you study Forman's papers, it's also there, although he does not use in his papers the language of dynamical systems. He only uses the language of graph theory, and he speaks about paths. But actually, implicitly, because when you look at the left picture, there is no much movement in this directed graph. You can start here and go here, and that's it. But actually, the point is that whenever you come to the end of an arrow, or you are at the singleton, you are allowed to move down to the boundary, with the exception of going down to where an edge comes in. So for instance, from let's take this edge, which is represented by this vertex. From here, you can go up to this triangle, and from this triangle, you can go anywhere to the boundary, except where you came from, except this edge, and so on. From a singleton, you can go anywhere to the boundary. This way, you get a directed graph, and actually also a multivalued map, which tells you where each vertex goes to. Unfortunately, this map is not continuous in any reasonable sense, which is a little bit strange. This is part of the reason we do not yet well understand the relation between the two approaches. There must be one, but it's still hidden from us. Okay, and the concept of Forman was just invented for Morse theory, but to study dynamics, we need a little bit more. Imagine that this is our cloud of vectors, which comes from this differential equation. The differential equation is here just to control that we understand what we are doing. But of course, the goal is to use it when you have no differential equation. And then you put a grid. Let's say this may be any grid. For simplicity, I just drew squares. And then you see that it does not fit to the Forman's concept because, for instance, this is a two-dimensional cell, and you would like to pair it with this edge, and with this edge, and with this edge. So it would be not a partition. So you need a slight modification. Actually, this would be the picture, but let me go back. Maybe I skip this. To this definition. A combinatorial multivector field, so this is now an extension of the Forman's concept, on a finite topological space is a partition of the cells of the space into locally closed sets. I said that locally closed means the same when you use for a finite topological space, when you use via Alexandrov this poset structure, it means that it must be convex. Convex, it means, for instance, that okay, so maybe it's still better to go back here. Sorry. So now I draw my collection of cells. Just I put them separately to see that these are a combinatorial object. 4 vertices, a couple of edges, a couple of triangles, a finite collection of cells. But if you want to avoid the language of finite topological spaces, you can take again the union. So this is now the union here. And you can even forget about the structure, and you can use the topology in Rn of this union. And I say that a set is locally closed or convex when you use the other language, whenever the mouth, which is the closure of your union, minus the union itself. So in this case, this is this red piece here. Whenever it's closed, you see here, it's like in the Wajewski theorem, and this connection to Wajewski theorem actually is not accidental. Actually, it's quite deep, but maybe not visible yet here. This is an example of a locally closed set. This set to the left is locally closed because the mouth is closed. And you can rephrase this using this poset structure, is that whenever there is, for instance, this vertex here, this vertex, and this triangle, everything in between, so this edge is both below the triangle because it's the face of the triangle, but about the edge because about the vertex because the vertex is a face of the edge. So the edge must also be in the set. So this way you test for convexity, and this is equivalent. Okay, so now our multivector fields are just a partition into these locally closed or convex or multivectors, as we call them. And then you can again draw these by putting arrows from lower dimensional cells in the same multivector to higher dimensional cells. So this is the dynamical representation of the partition, and this is more classical partition representation of a partition, where each set is drawn separately in the partition. Okay. How does it go back to the Forman theory? Actually, it's easy to check that singletons and vectors in Forman theory are actually convex. It's easier to test to see they are convex than they are locally closed, but they are both. So this is really an extension, this concept. And then you have again this multivalued map or directed graph, whatever language you prefer, with this implicit arrows, which let you go always back to the boundary. So your directed graph is a dynamical. This is, by the way, for those familiar with the Lorentz system, this is the combinatorial representation of the Lorentz attractor. Let me skip this part. This is about how you can construct such a combinatorial multivector field from a cloud of vectors. So there is a nice theorem and algorithm which lets you do that. So whenever we have a cloud of vectors, we can associate with this combinatorial multivector field. So this is another example, a differential equation where we just divided the space into squares. And it would take time to explain this picture, but there are those multivectors. You can see them here. There is one here and so on. They are not always the same. This is like in Forman, just a vector. This is a multivector. This is just a singleton here. But the colors actually represent these periodic trajectories. This green one is actually an invariant set here and represents this attracting periodic trajectory. The blue one represents the repelling periodic trajectory in the original picture. So you can just grasp this dynamics in this combinatorial model. And the whole point is that you can grasp this together with the Conley indices, because there is, let me skip that, there is Conley index in this case defined. How do you do that? So in this simple example, you have just a periodic trajectory. The convention is that you follow the Forman pictures. You only draw these explicit vectors, which come from partitioning. Just to keep figures simple, the implicit vectors, which tell you that you can always go to the boundary, are not drawn, just to keep the figure reasonably simple. So this is this green set of cells is a periodic trajectory, because you go along the explicit vector from this edge to this cell, two-dimensional cell, and then from this cell you can go anywhere to the boundary, but we pick up this one. Then there is no other choice but to go up, and then we have choices. This is multivalued, but we can also this choice and so on. So this way we have a closed path in this directed graph. This is actually an invariant set, because you can go on forever around this closed loop. And actually, this is an isolated invariant set. And its Conley index is, you take its closure and relative to its mouth. So here comes this, what I already mentioned, that why this finite topology is useful here. We are used, and for us it was for many years a mental obstacle. Then we tried to do something like that already 20 years ago with Konstantin. But at that time, somehow we tried to enforce that in our combinatorial dynamics, the isolated invariant sets are closed sets, because they are compact in the classical theory, so they are closed. So we expected them to be closed also in the combinatorial theory. But actually, the closedness follows from compactness under the Hausdorff axiom. Without Hausdorff axiom, compactness does not imply closedness. And actually, in this combinatorial theory, you have to accept that isolated invariant sets need not to be closed. It's even more, the topology corresponds to the attracting repelling behavior. Attractors are isolated invariant sets which are closed. Repellers are isolated invariant sets which are open. And isolated invariant sets which are neither closed nor open are neither attractors or repellers, like a saddle. In this case, this one is actually open. So this is a repeller, and we see this because we can actually choose another path. We have this multivalidness. So for instance, we can jump from here to here and then follow another trajectory like here, but we'll never come back to this green trajectory because it's a repeller actually. And the Conley index turns out to be take the closure. So now it's everything here, all the cells in the boundary, and take them out, and the mouth consists of these edges and vertices in the boundary and this one vertex here inside. You can actually compute this homology via McCord's theorem, and it's exactly the Conley index of a repelling periodic trajectory in the plane. So this combinatorial Conley theory for combinatorial multivector fields is available as a preprint. It's not published yet, it's submitted. And what is nice in this case that we can also do here persistence of the Conley index. So this is another paper presented in the Sausage Conference, the conference of the Society of Computational Geometry, the previous year with Tamal Day and his student Ryan Slechta. Namely, when you have now, we will look now at a family of dynamical system, actually, again, family of vector fields, but we discretized them. We constructed these combinatorial multivector fields. In this case, this is just a supercritical Hopf bifurcation, where we looked at the combinatorial models of this supercritical Hopf bifurcation. And so this means that there is a fixed point which is repelling inside, and then a periodic trajectory which originally is very small, and then it's growing, and our isolating neighborhood is fixed, so it grows so much that at a certain moment it goes out of the isolating neighborhood, and at that moment this box isolates only the fixed point. Here it still isolates the fixed point inside, the periodic trajectory, and all the connecting orbits in between. At certain point, not marked in the picture, this periodic trajectory is tangent. There is internal tangency, the first internal tangency, which causes that you lose isolation. There is one moment that there is no isolation, and then the Conley index changes from attracting fixed point, because here you see just the periodic trajectory and everything in between. Here the periodic trajectory is gone and there is only this repelling fixed point left. So you see one red bar which corresponds to the zeroth homology, and then this bar is gone, this bar dies, and another bar is born in dimension 2, which represents this repelling two-dimensional fixed point. There are more examples not yet ready to present, when you actually see situations when one bar dies, but another persists through. So the Conley index is for a moment not defined, but a part of the Conley index persists and goes over to the other side. Okay, my time is gone. So very briefly, you can do also in this setting the persistence of Morse decomposition. I had an example, but let me skip all the rest and let me go to the references. So summarizing, it seems that there emerges a nice combinatorial version of the Conley theory, which may be combined, at least in some situations, not as deeply as we would wish, but deeply enough to give some useful result, combined with the persistence theory. So there is a hope that this topological data analysis may be usefully extended into the study of dynamics, not only from samples, from sampled dynamical systems. So thanks a lot for your attention.
Yeah, thank you very much. Thank you. Any questions?
Well, hello. Maybe I can ask a question. So I guess all of this. So I'm Kalle Timperi. I'm at Imperial, working with bounded noise. So I was wondering if you are considering any kind of, noise in the data. Let's say you get the time series and.
Yes. So at least in the sense that we try, whenever you have bounded noise, we do have examples. I even shown you some where this bounded noise, when it's reasonably bounded, then you still see the same results. So when you take this data and you add some noise, then actually it persists from the exact situations to the noisy situation to some extent. And this is not unusual, because the Conley, what makes so great the Conley theory is its stability to perturbations. When you perturb, the Conley index is preserved, and we do the same here, but it's too early yet. We think about it, but we have no result yet. In the persistence theory, they studied this stability question, and they actually proved that this map which sends persistence module into the persistence diagram or barcode is Lipschitz continuous in some sense. You have to put certain metrics. And so whenever you change your data a little bit, then the persistent diagram will change a little bit. We see something similar here, but there are still technicalities how to, for instance, prove a similar theorem for the persistence of the Conley index. But we work on that, and we strongly believe something along these lines is also true. We see this on the examples, and we rather think it's more just technicality than a serious problem.
Okay.
But who knows? Who knows? As long as you have no proof, everything may happen.
Of course, yeah, but it makes sense. Yeah. Thanks very much. Very nice talk. Yeah.
Thank you.
Any other question? Yeah, maybe a slightly related question about when you add noise. I mean, so when you add noise, I mean, you said that things don't change by adding noise, but if you increase the size of the noise, I mean, did you like find any sudden changes that may happen, a sort of like bifurcation behavior that is depending on the amplitude of the noise?
Yes, so of course, this is what happens. We haven't studied it too much yet. This is one potential next direction, but we would expect this to be visible in these bars. So the example I gave here, let me go back. This one. Here, the persistence is with respect to the continuous change in the dynamical system itself. But there is no fundamental reason that actually you could do right now this theory as it is set up to study the persistence when you just keep adding more and more noise. So with respect to the noise level. And you can still try to see what happens with these bars. We haven't done that yet, but at least all the tools are ready, and this is just there are so many directions to study that some things have to wait. But that would be a very natural next experiment, just to look at the machinery is ready, and I would expect that you would see just some isolated invariant sets getting glued together. So because of the noise, you can get artificial connections between the Morse sets, which will cause them being glued together, and it should show up very nicely in these persistence bars. But these are my expectations. We haven't done that yet.
Okay, yeah, thank you. Yeah. Any other questions? Yeah, all right, yeah, it seems there is no options. Yeah, okay, thanks a lot again for the nice talk, and looking forward to
Thank you.
another time. Yeah,
Thank you, everybody.
Thank you. Thank you.
Thank you.
Yeah, thanks. Bye-bye. Take care and stay safe. Yeah, thank you.